Okay, welcome back everyone. In this video we're going to start talking about lenses, and we'll look at how lenses are similar to and different from mirrors. So the basic idea behind a lens is that lenses function using refraction. So that is that light bends as it enters a lens. So lenses can be made of many different materials, and sometimes when you are buying glasses they'll ask you if you want a high index lens, and so that just means do you want plastic or glass that has a very high index of refraction. And so of course what we know is that if I have a little bit of a surface right here, and if I have a beam of light going into that surface, well, Snell's law is going to apply. So what I need to do is try to construct some sort of a normal, okay? And rather than the ray of light keep going the way it was, it's going to bend. If this is air and this is some sort of glass, glass is about 1.5 or so. Going from less dense to more dense, the light is going to bend towards the normal, so something kind of like that. So if we were to measure theta 1 or theta incident and theta 2 or theta refracted, that's what would happen. If we then put a second surface right here, so that we're talking about pieces of a lens, well, the same thing is going to happen. Again, what we do is we construct the normal, and the normal looks, perhaps like that. And when that ray of light hits the normal, let's pretend like it's pretty close. When it hits the boundary, it's going to bend away from the normal, and so now this time, rather than traveling in a straight line like this, it will bend away from the normal and go this way. So really what lenses do is they bend light twice, and so that's why we don't always draw these middle rays with what's happening, but parallel rays come to a focus for lens. I'll show you a much better example of that in a moment. Okay, so lenses do have two surfaces, and this makes things a little bit more complex. So you can have one surface outward and another flat. You can have one surface inward and the other one flat. And whenever it's flat, it's called plano. So for example, this one would be plano convex, and this one would be plano concave. And of course, you can have lenses that have both sides convex, so this is biconvex. Okay, you can have both sides concave or biconcave. And then you can even have combinations where you have one side is convex and the other side is concave. So this is concavo convex or something like that. And then of course you can have the opposite of that too. And the thing is, this gets very complicated mathematically very fast, so we're just going to stick with these two guys here. And so when we say that we have a convex lens, you should think about it as having two convex sides. And the same thing with a concave lens. If I say concave from now on, I'm meaning I have two sides that are concave. Okay, so that's important. And the other thing that we're going to assume for the purposes of what we're doing right now, assume that the lens is thin. So not meaning that it, did a Jennifer Hudson, it's on Weight Watchers or whatever. No, what we mean by this is that the actual thickness of the lens in the center is pretty small compared to the height of the lens. Okay, so if we say that it's got kind of a diameter of D and some height of A, I don't want to use other letters. We just want to say that D is pretty small compared to A. Okay, so once you get out of that region, once the thickness of the lens is more on a par with the size of the lens, well, then you're going to have to use a different equation. And so the mirror equation that we used previously, namely that 1 over f equals 1 over do plus 1 over di, well, that's when we have a, quote, thin lens. Otherwise, we can't really use it. Okay, now the other thing that you should know about lenses is that lenses behave inversely of mirrors. I don't know if that's phrased exactly correctly, but what I mean by this is that a convex lens works the same way mathematically as a concave mirror. Okay? And likewise, a concave lens works exactly the same as a convex mirror. And we'll see some examples of this in a moment. But let's just talk for a few minutes about the different images that we can get. So first of all, we'll start with concave lenses. Concave lenses, because they work like convex mirrors, they always produce, see if you can guess, if they work like convex mirrors, they always produce virtual images, which are smaller. Smaller than the object. So, in other words, di is less than 0, so it's a virtual image. There's a negative image distance, and the absolute value of the magnification is less than 1. Okay, so that's concave lenses, and in the next video I'll do some ray diagrams and kind of show this. Okay, convex lenses, they basically function exactly the same as a concave mirror, and so what they do is dependent upon where you're at. So first of all, if the object is beyond the center of the mirror, twice the focal length, then it's going to be real, it's going to be inverted, and it's going to be reduced. So in other words, it'll be a little bit smaller. That's option number 1. And this is the exact same as what we saw for concave mirrors. Option number 2, if we are in between the center and the focus, we still have a real inverted image, but now the magnification will be greater than 1, absolute value. And just as an aside, when do is equal to 2f, then you basically get do is equal to di. And I'm not going to prove that right now, but you can plug it in and see why that has to be true. And then finally, the third thing is that if do is less than f, so if we're inside of the focus, then we're going to be talking about a virtual, upright, and enlarged image. Okay, so this is the same again as a concave mirror, and so if you have any questions about how those work, you should go back and review. But very quickly, to finish things up here, let me show you, that's my screencast That's how I record these videos. Here's a PhET geometric optics um, animation or applet here. And so what we're looking at are the principal rays. Again, let me just trace this out to show that it's very similar. The first ray enters the lens going parallel, and it passes through the focus. Now, what I have to point out is that a lens will have two foci, two focuses. Okay? The first one right here, the near focus, corresponds to the curve of the back of the lens. Okay? This guy right here on the far side represents the focus corresponding to the front of the lens. Okay? And just like concave mirrors have positive focal lengths, okay, convex lenses have positive focal lengths. That means that concave lenses have negative focal lengths. Okay, the second ray is the opposite. It's the one that goes through the focus and it emerges parallel. And the third one is the one that goes through the center, and instead of reflecting back, it keeps on going. Okay? Now the one that goes through the center, by definition, will basically strike the lens. If it goes through the center, it'll strike it at a 90-degree angle to the lens, and so therefore it will not be refracted at all. It'll keep on going in a straight line. Okay, and finally I can show you that right now, at least, it looks like the object and image are almost the same size. Okay, if I go inside of the focus, you can see that I have 1, 2, 3 rays that are diverging that form a virtual image, and more details on those rays a bit later on, but just to show you the behavior. And if I go to the focus itself, we have the same problem that we did with mirrors, in that all of the rays are parallel. None of them converge at all. And of course out here we have a real image. Okay? And so this is a fun app to play with. You can change the object to see how the orientation works. There's our famous arrow. Okay? And that's about it. Okay? So next time I'm going to do some ray tracing and show you how it works for a couple of different lens situations.